So what we'll check out here is a problem where we want to sketch a graph of this function. We want to do it by hand, and we want to determine all of these features of this function before we try to sketch its graph. So we'll just kind of compile everything on this screen and then try to wrap things up by sketching the graph over here in this empty space. It's going to take a bit of time to complete that analysis though. So what I want to start with for this function is going to be its domain. So the domain of this function would be the x values that you are able to plug into the function. So in this case we have e to a power, and e to a power is always defined. However, if you look at this power, the power itself is not always defined. When you put a 0 here, 1 over 0 squared, 1 over 0 is undefined. So the domain of this function is going to be negative infinity to 0, and then from 0 onward to infinity. 0 is not in the domain of the function because 0 makes the exponent undefined when you toss 0 in place of x. So we have a domain that has everything except 0. Next, what we want to check out is we want to check out our asymptotes. So I'm going to go with vertical asymptotes first here. And if we're looking for vertical asymptotes, what's going to be true about a function that has a vertical asymptote, like if a function has a vertical asymptote, it's because the function has a y value that goes up to positive infinity or down to negative infinity on either side of that vertical asymptote. So here we want to check one limit to start off with, and that's the limit as x approaches 0. The function's undefined at 0, so we have to be undefined at an asymptote, and then if this limit turns out to be either infinity or negative infinity, we know we are going to have a vertical asymptote for this particular function at this x value. So when we put 0 into the function, we get e to the 1 over 0 squared. Now, when you have an expression that is undefined, as this one is, it's a signal that you are going to get infinity or negative infinity for your limit, but you're going to want to check one-sided limits to determine which. So I'm going to break this up into two separate one-sided limits. I'm going to approach 0 from the smaller side. When I approach 0 from the smaller side on this function, what I end up getting in this denominator is a small positive. Right? If I put a small positive here in place of this x and I square it, it stays a small positive. 1 divided by 1/1,000,000th, that's going to be like 1 times 1,000,000 over 1 times the reciprocal of that small fraction. And so that's going to be a huge value, and the huge value in this case is going to be positive, and that's going to be the exponent on a base e. And if you think about the graph of e to the x, graph of e to the x looks like this. E to the infinity, when x is way over here, your y value is way up here. So e to the infinity is infinity. This tells us we do have a vertical asymptote at x equals 0. We'll see if this vertical asymptote is a symmetric one. You know, this one we have positive infinity on one side and negative infinity on the other. We'll see what's going on both sides of 0 with this function. So when we check the limit on the other side of 0, we put a small negative here, negative 1/1,000,000th. Well, we square that and it becomes a small positive. So we end up with 1 over 0 from the bigger side again. That's still going to be e to the infinity, which gives us an answer of infinity. So we actually go up off our graph to positive infinity on both sides of 0 for this function. We do have a vertical asymptote at x equals 0. So vertical asymptote is there. Does this function have any horizontal asymptotes? So when you're checking for horizontal asymptotes, they're going to exist for one of two reasons. A lot of the time it's both. But if you look at this graph right here, this graph has a horizontal asymptote, it would seem, because when we have a very negative x value, when x is way over here, the y value on the graph is approaching maybe the y value of 1. On this side, as we approach positive infinity, when x is way over here on the x-axis, it would seem our y value is approaching 0. So you want to check two limits to determine whether or not a function has horizontal asymptotes. You want to check the limit as you approach infinity. You also want to check the limit as you approach negative infinity. So here, if we check the limit as we approach positive infinity, we want to put positive infinity in place of that x, and then it's going to get squared. So we put a big positive here, we square it, it becomes an even bigger positive. 1 over infinity, well, that's 1 over 1,000,000,000. That's essentially 0. This exponent is becoming closer and closer to 0 as this x grows and grows and grows. So e to the 0 is going to give us a value of 1. So this function does have a horizontal asymptote on the right edge as x is going to positive infinity at y equals 1. If we check the limit on the other side, we're going to get the same value, because the only thing that changes is when we put negative infinity, a negative that's far from 0, in place of the x, but then we square it, so I can't see the function anymore. You know, we're going to put a negative that's really far from 0 here, negative a billion. We're going to square it. It's going to become positive, and it's going to get even further from 0. So this is going to be 1 over positive infinity again. 1 over positive infinity, like we said a minute ago, is going to get closer and closer to 0 as the denominator grows and grows. E to the 0 is 1. We have a horizontal asymptote on this graph at y equals 1. So we're ready to go ahead and try to do some of the work that would involve the first derivative here. We know our domain, we know our asymptotes. Now we're ready to go ahead and do an analysis of the first derivative. So the function in this case, again, is e to the 1 over x squared. If we want to build a sign chart for the first derivative to determine where our function has local maxes, local mins, where it's increasing, where it's decreasing, first order of business is obviously to take the first derivative. So the derivative of e to a power is normally e to the x, but when we use that derivative formula with the chain rule like we have to do here, since this is an inner function, we need to put that inner function in place of the x. And then we're going to have to finish our chain rule by multiplying by the derivative of 1 over x squared. Well, if you think about 1 over x squared can be written like this. And the derivative of this is just going to require a power rule. We're going to get negative 2x to the negative third. Right? So I'm thinking about writing this as x to the negative second. The derivative using the power rule only gives me this, and that can be rewritten as negative 2 over x cubed. So the derivative of the inner function, and the way that I'm going to finish my chain rule here, is by multiplying by negative 2 over x cubed. I'm going to simplify this a little bit. You know, I'm going to take this fraction, e to that power over 1, and multiply it by this fraction. So that's just going to require me to do numerator times numerator, giving me negative 2e to the 1 over x squared. And then denominator times denominator is just going to give me an x cubed. So there's my first derivative. I want to build a sign chart for my derivative, so I'm going to have to figure out when my derivative is equal to 0. What are my critical numbers, basically? So if I set this derivative equal to 0, if I set negative 2e to the 1 over x squared equal to 0, I'm going to try to isolate this x. I'm going to divide both sides by negative 2. And that's just basically going to make the negative 2 go away, because 0 divided by negative 2 is still 0. And then if I take the natural log of each side, I'm going to get 1 over x squared on the left, and then on the right, I'm going to have the natural log of 0. Well, the natural log of 0 is undefined, so although we had to consider setting that numerator equal to 0, we don't have any places where this first derivative equals 0. Do we have any places where the derivative is undefined? Well, if you look at the denominator there, x cubed, you set that equal to 0, and you get x equals 0 as the solution, right? Set this denominator equal to 0. Also, set this denominator equal to 0, and x equals 0 makes both of those denominators 0 simultaneously. This is not a critical number, however, though, because this is not in the domain of the function. It is a place where we have to allow the possibility for the first derivative to change signs, though. So my sign chart for the first derivative is going to have the only split value at 0. And we want to check what the sign of the derivative is with using an x from over here. So if we take an x like negative 1, put negative 1 in place of these x's. Negative 1 here gets squared. It's positive 1. In the numerator, I'm looking at negative 2 times e to the first. That's a negative numerator. And then if I have negative 1 here, cube it, it stays negative 1. So a negative divided by a negative is going to give me a positive derivative. And on the other side of 0, at a test value like 1, if you put 1 here, you're looking at negative 2 times e to the first, so that's negative, and then 1 cubed is positive 1. So a negative divided by a positive is going to give me a negative value for my derivative. So what we can conclude about the first derivative is that it's positive from negative infinity to 0, meaning our function is increasing on that interval. And then from 0 onward, the derivative is negative, so our function is going to be decreasing there. We don't have a maximum at 0 because the function's undefined at 0. That's why I've poked that little hole out of the number line there. So increasing here, decreasing there, no maxes, no mins. We'll do the work for the second derivative and try to wrap up with the sketch of the graph in the second part of the video.